Hey everyone, this is our lesson on types of chemical reactions, and by the end of this lesson, you should be able to analyze the law of conservation of matter and how it applies to various types. And we're going to focus on learning about these various types today. So first, let's talk about chemical reactions themselves. And that is defined as when a chemical change occurs, transforming your reactants on the left side to your new products on the right side. And when we look at these, we have to understand how to predict products. So as a chemistry class, you do have to understand how to predict products because I may just give you the reactants. To do this, though, you need to use your reference packet because it will tell you or help you predict products for all types of reactions. So I'm going to kind of show you, and obviously if our reference packet changes, I'll update it whenever we're in class. But you have a page in your reference packet that is called Guidelines for Predicting Products of Chemical Reactions. So you need to find that page because it will tell you everything that you need to know. When predicting products for a single replacement reaction, which we'll discuss in a minute, you're going to use the activity series that's also in your reference packet. There is one for metals and one for halogens. In your reference packet, I think we only have the one for metals, but for halogens, that's your group 7A. They're more reactive from top to bottom. So just look at that. But we have to pay attention to the single element on the reactant side to know how to read this. And the product side to know how to read your activity series. And then let me shrink there we go. And then when predicting products of a double replacement, you have the solubility rules that are also in your reference packet. And all of these we tried to put on the same page. So look for those. And then for double replacement, you can have three different types of products. So you can have a liquid, which is water, H2O. You can have any gas that forms, or a precipitate. So that is going to be the slightly soluble solid that comes out of solution. And don't forget to balance. So just because you can predict the product does not mean you don't still have to balance, which you will have to do on your mastery checks as well. So let's get into our first type of reaction, which is a synthesis reaction. And you define this as two reactants which form one product. And the reason I have one product underlined is that's what's a dead giveaway that we have a synthesis reaction. Our general equation for this is A plus B yields AB, because the two individual reactants came together to form one product. And a real life example of this in your notes is 2Mg plus O2 yields 2MgO. So as you can tell, I did balance this. Our dating example here is the hookup. So, two individual people start dating. That's what's happening here with a synthesis reaction. And then to predict products, we're going to walk through this one together. You have to make sure to balance when necessary as well. So we have lithium oxide, Li2O plus H2O. So I will pause here. You need to review balancing before you get too far. You also may want to review writing chemical formulas in case you still struggle with that. But we're going to take these two and we're going to combine them. And, this looks kind of difficult because they're not just elements bound together like they were in a real life example. These are compounds. So if you look at your reference packet, so here in this specific reference packet, we've got our guidelines for predicting products. And you see I've colored it out because it was a typo on my part. But for synthesis reaction here, you can have a metal oxide. Okay, it says MOH on yours, so please scribble out that H. So metal oxide plus water yields a base. Remember, a base is an OH. So if you know that, we should know that our product is going to be LiOH because that's our base with the metal that, remember, it's a metal hydroxide. So we took this metal and then we knew based on rule 1A that it was for your reference packet. Again, this could change, so just bear with me on that number. But that forms a base there. So now our job is to balance. We've got 1H on the left, on the right, 2 on the left, 1 O, 2 O's, 1 Li, 2 Li's. So we're going to stick a 2 out front, which would then balance the entire equation. Okay, so make sure you will start doing you-dos for predicting products and balancing for the rest of these examples. All right, so now let's talk about decomposition. This is the exact opposite of a synthesis. So here, the dead giveaway is we only have one reactant. So you see one compound and then an arrow. And from here, we will produce two products. I put some asterisks here because you could actually produce more than two products. And these are can be pretty difficult to predict if it's not just a basic, like, two-element compound, KCl. NABR, you know, those are only two elements. It's easy to know how those break up. So you will definitely want to pay attention to your reference packet for this part, okay? So our general equation is the opposite of synthesis. So AB yields A plus B. Our real life example is carbonic acid breaks down to form water and carbon dioxide. So here you could tell this did not break down into just two elements. This would be basically example 2A in your reference packet. It doesn't have an acid there, but it does have a metal carbonate, and this could be considered a metal carbonate. Okay, we have our dating example here. So since it's the opposite of the hookup, that would be the breakup. And our real life example that is a you-do is for Na2CO3. So remember that CO3 is a carbonate. So use your reference packet and try to figure this out. Make sure you balance. Pause the video and try that. All right, so now let's jump into single replacement. The definition for single replacement is you start out with an element in a compound, and then you develop or produce a new element, a new single element in a new compound. So our generic example here is AB plus C yields CB plus A. So as you can tell, the C and the A switch places, okay? So a real life example of this, we've got Cu plus AgNO3 yields CuNO3 plus Ag. So our metals switch places here. And it all depends on what that single element is. So this is known as the cheater because the metal was originally, or I'm sorry, the non-metal was originally with one metal at the beginning, but it's with a new metal at the end. And then you're going to predict the products for this one. Remember, this is single replacement, so you have to use your activity series, okay? And to use your activity series, I'll give you a hint. We know that Na is our single element. It would deal with the first element in the compound of water. So you need to compare those on your activity series. Whichever one is highest up on the list will do the replacing, okay? So if Na is higher than H2, Na will replace H2. But if H2 is higher, nothing will happen. So pause the video and try that to balance. All right, so now let's go into double replacement. This is defined as two original compounds changed to form into two new compounds. AB plus CD yields CB plus AD. So you can just switch the beginnings if you want. Some people will do this where they partner the inners with the outers, like they'll partner the inners together and they'll partner the outers together. So as you could tell, C and B go together, and then A and D go together. So inners and outers, if that helps you to know how to predict your products. A real life example here is ZnI2 plus PbNO3 yields PbI2 plus ZnNO3. So remember, we can have three different types of products here for double replacement: a gas, a liquid, or a precipitate. So you do have to list your states here. So that is very, very important to list these states because that tells us what kind of product we're forming. And if you see, we formed a solid here. So just make sure you pay attention to kind of how to write these. You've got to use your solubility rules if you make compounds and one of them is not clearly water or a gas. If you see a CO2, we know that's a gas, so that's your different product. If you see water form, we know that's a liquid, so that's your different product. But if you see compounds like this, you've got to use your solubility rules. So for example, we would look at this and we would say, okay, our two products are PbI2 and ZnNO3. You can look at these rules, okay? So as you see right there, they're called the solubility rules, okay? We look usually at the second element. So we're going to pay attention to the I and the NO3. So NO3 is nitrate. The first rule in here says all nitrates, acetates, ammoniums, and group 1A salts are soluble. So no matter what that's partnered with, that's going to be aqueous. Okay. Then we can look at the second one just to check. And it says we're looking at iodine. So we have a rule on here that says all chlorides, bromides, and iodides except silver, lead, and mercury 1. So they are soluble unless they're partnered with one of those three. And we are partnered with lead here, which means that it's going to be insoluble. Okay. This is called the switcheroo because your partners, two couples switch partners. Okay. And then you're going to try to predict these products using your solubility rules. And this one, I think, in all actuality, does not apply to the solubility rules. But go ahead and switch your products just to see what would form. And our last one is combustion. This is everybody's favorite. So the generic example and definition are the same. So it would be a hydrocarbon plus oxygen gas yields CO2 plus water every time. A real life example here is taking a sugar and burning it in the presence of oxygen. You obviously have to have some sort of spark, but oxygen, the biggest key thing here, oxygen has to be a reactant. It has to be. Without oxygen present, something cannot burn because that's the fuel for a flame. Okay. Our dating example here is the heat. And I want you to go ahead and try to predict these products. Now, make sure you're balancing all of these, okay? So go back and look at your examples, make sure they're balanced. But one thing to know with types of reactions is they don't always just fit neatly into one category. So the example that was under synthesis, Mg plus O2 yields 2 MgO, that one actually classifies as a combustion as well. But I will be nice enough to only give you if it's a multiple choice, only one of the possible answers it could be correctly. Okay. So just be aware you're not going to fit these all nicely into individual little things, but we